guys, welcome to tutorial 1 under node voltage method. In our previous videos we learned about the mesh current method, and we learned that in dealing with a mesh current method we first of all have to identify the number of meshes in the given circuit. After identifying the number of meshes, we assign current to the individual meshes, then we write KVL in the meshes. So the same thing applies to this method. From the name, node voltage method, it means we are interested in finding the voltages at the individual nodes. So in dealing with this method, what you have to do first is to identify the number of nodes you are dealing with. Okay, so in this diagram, ask yourself how many nodes do we have? And a node is formed when two or more branches meet. So looking at this diagram, we have a node here. This junction is a node. A junction is the same as what? A node. Why? Because we have three branches meeting here. We have one branch here, another branch here, and another branch. So we have a node here. Let's say the first node we've identified. Looking at the bottom here, we have another node. So let's say this one is what? The second node. So now we've identified the number of nodes in the diagram. So for us to use this method, we have to set one of the nodes to be the reference node. After identifying your number of nodes, there can be 3, there can be 4. So after you see the number of nodes that you have, set one of them to be your reference. So between 1 and 2, we are going to set one of the nodes to be our reference node. Okay, so if that node is our reference node, it means the voltage at that node is what? 0. First of all, identify your number of nodes. Let's say we have one node here, another node here. So like the mesh current method, after identifying the mesh, you assign current to the mesh. So now after we've identified the node, let's assign the voltages to the node. So let's say the voltage at this node is what? V1. There is a voltage also at this node, V2. Good. So between these two voltages, we are going to set one of them to be the reference. So preferably, we use the down node, the bottom node, to be our reference node. And if it is the reference node, it means the voltage at that node is equal to 0 volts. It means it is grounded. So in this diagram, we will say, let node 2 be the reference node. So now it means the voltage at the node 2 is equal to what? 0 volts. So what you should know that you start with a number of nodes in the diagram, then you set one of the nodes to be your reference node. It means the voltage there is known. Now we know the voltage here to be what? 0 volts. So we are left with what? V1. Now the V1 becomes the non-reference node or the unknown node. Alright, so what you have to do next is to write Kirchhoff's current law at the non-reference node. Don't forget, one of the node is reference, so we know the value now. So we are going to write KCL at the non-reference node. And KCL deals with what? Current. So it means we have to assign current to the branches. That is what? Entering, or that is pointing to that non-reference node. So let's assign current on the branches. In this diagram, the current direction were not given. So you can assign the current on the branches in any direction that you want. So on this branch, I'm saying there is a current I1. On this branch too, I'm saying there is a current moving on that branch. Let's see what? I2. Let's say on this branch too, there is a current I3. So we've assigned current to the branches. So we are going to write KCL at the non-reference node. So we have KCL at node 1. So back to our KCL video, we know that KCL states that the sum of current entering is equal to the sum of current leaving. So we have I1 is equal to what? I2 plus I3. That's the KCL at node 1. So after writing the KCL at the non-reference node, the next thing is to express each of the currents in terms of its node voltages. Express each of the currents in your KCL equation in terms of what? Node voltages. What do we mean? Let's say we have a resistor like this. Okay, we have this resistor and we have a voltage at this point, let's say VA, we have what VB, and we have resistor what R, and there's a current moving through the resistor. We know that from Ohm's law, I is equal to V over what R, but this V here is called the potential difference. So it means that V is actually the difference between two voltages. So it's like V1 minus V2 that we've done the mathematics, and we have what V. So looking at this diagram, we know that current through a passive element starts from the highest potential to the lowest potential. It means current will start from where the voltage is big to where the voltage is what less. So when I have this and I want to calculate I is moving from which node? It's moving from node voltage VA, and it is traveling all the way to what? Node voltage VB. It means my V here is what the difference between VA minus what? VB, where the current is starting minus where the current is going. So I have VA minus VB over what? R, and R is the resistor on that branch over R. You have another scenario. Let's see. I have a resistor, I have a voltage source, and I have two nodes. Let's say node voltage VA, node voltage VB. Let's say I have resistor, voltage Vs, and resistor what? R. And I want to find current I. So we know I is what? V over R. But on this branch we have three voltages. So it means we have to find its equivalent and divide it by what? The resistor. So don't forget, if you want to know the V, always put it at the back of your mind. It is the node the current is starting from minus the node where the current is what? Ending. So now, where is the current starting from? It is starting from VA. So I have node voltage what? VA minus, where is the current going? It is going to VB. So minus node voltage what? VB. But don't forget, on this branch we have another voltage source, Vs. So let's see, when this current is flowing, it will enter this voltage source at the positive and leave where? The negative. So since it is leaving the minus, it means we are going to subtract that voltage from the V. So it means this becomes minus what? The Vs over the resistor R. So you check that voltage on the branch. If the current direction is leaving the negative, you have to subtract that voltage from our numerator. Assuming the current, the voltage is minus and plus. So in this case, it means the current will enter negative and leave the positive. So that one, we will first of all have our VA minus our what? VB. Then we check. The current will leave the positive. So we have what? Plus Vs over what? The resistor R. So that's how we express the current in terms of its what? Node voltages. So let's apply that concept in this diagram. So we are going to express the current that we have in the equation in terms of its node voltage. So let's see I1. Looking at this diagram, I1 is the current here. Don't forget, I said you can use the basis like this. The I1 is starting from a node and it is moving all the way to another node. So looking at this diagram, this is a whole complete branch. So the current is moving from here. The I1 is here on this same branch. The I1 is here, here to this point. So we can say that the I1 is starting from a node, what? V2. So we have what? V2. And it is moving all the way to which node? Node V1. So V2 minus what? V1. But don't forget, we met another voltage source on our way. And that current I1 was leaving what? The positive terminal of this voltage. So that means that voltage becomes what? Plus 20. Alright. Divided by what? Divided by the resistor on that branch. And that is what? 5 ohms over 5 is equal to. So we are just expressing this equation here in terms of what? The node voltages. So it's equal to what? I2. So let's check I2. I2 is here on this branch and it is starting from which node? V1. And it is going to which node? V2. So we have V1 minus V2 over resistor 10. You realize there is no other voltage on this branch, so we just have V1 minus V2 over 10 plus I3. So what is I3? I3 starting from which node? V1. It is moving all the way towards the reference node V2. So we have V1 minus what? V2. Is there any other voltage on that branch? Yes, we have another voltage. And where or which polarity is the current leaving? You realize the I1 is moving in this direction. It will leave the negative terminal of this voltage. It means you have to subtract. So we have minus 8 over what? The resistor there, which is what? 2 ohms. So we have 2. So now this is what? The equation or the load voltage expression of this KCL equation. So we are interested in finding the node voltage, that is V1 and V2. But we already know that V2 is equal to 0. So we can substitute that value in this equation. So if V2 is 0 here, then it means for this equation we have what? 20 minus V1 over 5, giving us what? V1 over 10. This is 0 plus V1 minus 8 over 2. So this expression or this equation is the same as this equation. So from here, how can we get our V1? We can multiply through by the LCM, which is what? 10. So multiplying through by 10, I have this place multiplied by 10, so I have 2. 20 minus V1 is giving me what? V1 plus 5 into bracket, V1 minus what? 8. So let's simplify this. I have 40 minus 2 V1 is giving us V1 plus 5 V1 minus 5 is 40. Good. So let's group like terms. I'm sending the minus 2 V1 to the other side. What would we get? We will get 8 V1 is equal to, I'm sending this one here, is equal to what? 80. So this implies that my V1 is equal to what? 10 volts. So my node voltage V1 is equal to 10 volts. Now you can also be asked to use the node voltage method to find the current in each resistor. Okay, so don't forget the current through the 5 ohms is I1, the current through the 10 ohms is I2, the current through the 2 ohms here is what? I3. So we can use the node voltage method to calculate these 3 currents. So after we found the V1, we know that our I1 from the diagram, we know that our I1 is equal to V2 minus V1 plus 20 over 5. So we can calculate for our I1. So I1 is equal to what? V2. Or we can use this expression because this is the simplified version of this one. So I1 is what? 20 minus V1 over 5. So we have 20 minus V1 is 10 over what? 5. So this one gives us 10 over 5, which is what? 2 amperes. So the current I1 is 2. We can find what? I2. And what is I2? I2 is what? V1 over 10. So we have V1 is what? 10 over 10, which is what? 10 amperes. So the last current is I3. And what is the expression for I3? I3 is V1 minus 8 over 2. So V1 is 10 minus 8 over 2, which is what? 2 over 2, and that is 1 amperes. So this is how to use the node voltage method. You first of all identify the number of nodes, assign voltages to the nodes, set one of the nodes to be what? Your reference. Then we will have n minus 1 nodes left. The next thing to do is what? Write Kirchhoff's current law at the non-referenced node. So after writing your KCL at the non-referenced node, you have to express each of the currents in terms of what? The node voltages. Like what we did here. Express each of the currents in terms of its node voltages. Then you solve the equation to get your what? Node voltage. So that's all about the node voltage method. So in our next video, we'll be solving much complicated circuits than this one. Thank you very much for watching this video.